Question 16. But(1,ene and but(1,3-diene are unsaturated compounds used to make many organic products. A. But(1,ene and but(1,3-diene have sigma bonds and pi bonds. Explain what is meant by the terms sigma bond and pi bonds. For sigma bond, it's head-on overlap of orbitals, head-on overlaps of adjacent orbitals. So if you have s orbital, which are spherical, so that's s orbital, this is your sigma bond. If you have a sp orbital, s and p orbital, that will be the sigma bond. Or we might have two p orbitals, that's p orbital, and that's the sigma bond. For pi bond, sideways overlap of adjacent p orbitals. Here's one p orbital, another p orbital overlapping sideways. For part 2, how many sigma and pi bonds are in one molecule of beta-1,3-diene? First, we need to draw the structure of the beta-1,3-diene, and from each single bond are sigma bond. A double bond is sigma bond and pi bond. So that will be sigma, 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 sigma. So there are 9 sigma bonds. And for pi bond, this is pi, pi, and there are 2 pi bonds. B. But(1,ene is reacted with hydrogen bromide, forming a mixture of saturated organic products. One of the organic products is formed in a much greater quantity than the other organic product. I. Outline the reaction mechanism for the formation of this major organic product. The structure of but(1,ene has been provided. Include curly arrows and relevant dipoles. So this reaction is basically applying Markovnikov rule. Markovnikov rule says that the hydrogen from the hydrogen bromide will go to carbon with the most hydrogen. So these two carbon, this carbon here has the most hydrogen, and this carbon here has least hydrogen, and then it's got carbon. So the hydrogen from the hydrogen bromide will go to this carbon, and then the bromine will go here. That will be the major product. So we got the hydrogen bromide, difference in electronegativity 2.8, 2.1. Therefore, we got delta plus and delta minus, delta plus. The electron here, the pi electron here, will attack this hydrogen, and this will break. So this is fusion and this is fission. That's the attacking and the breaking, forming a new product here where the hydrogen goes there, and this is a carbon cation, positive here, and a bromide ion. The next stage is where the lone pairs here will attack the carbon cation to then form the major product. And this major product is formed due to Markovnikov rule. The minor product will be so we swap these two here, where the bromine goes there and the hydrogen go there. That will be the minor product. Otherwise, this is the major product. Explain why one organic product is formed in a much greater quantity than the other organic product. Well, we're looking at the intermediate formation of carbon cation. The tertiary carbon cation is more stable than the secondary carbon cation, which is more stable than the primary carbon cation. The tertiary, if you have a carbon with a 3R groups, this one is a secondary carbon cation. So that one here, this is an R group, and the H is gone here to make this one a methyl group. The H is gone there to make that a methyl group. So you got 2 R groups here, R1 and R2, and that is an inductive effect of donating electron to stabilize the carbon cation by inductive effect. And the other product that could form is a primary carbon cation, which is donating electron, but this is not a methyl group. So this is a primary because it's got 1 R group. This one has got 2 R groups here. So that's secondary, and this one is primary carbon cation. The secondary is more stable than the primary carbon cation. And so we can say more stable intermediate is the secondary carbon cation. The major product forms from the stable secondary carbon cation. Part 3. Butyl 1,3-diene is reacted with an excess of hydrogen bromide, forming a mixture of saturated organic products. How many saturated organic products could be present in this mixture? So we could have, this is the butyl 1,3-diene, and when reacted with hydrogen bromide, we could get a product where the Br goes there and there. So the Br goes here and there, that's that one. Or we could get a product where Br goes here and here. So that's another one. And the rest are hydrogens and hydrogens. And the final one would be where Br goes here and Br goes there. So we have 3 different possibilities. So we could put 3 there. 16C. A student thought that butyl 1,3-diene can show stereoisomerism. The student drew out skeletal formulae for the stereoisomers of butyl 1,3-diene. See Part 1. Explain the term stereoisomerism. Well, stereoisomerism is when you have same molecular formula, same structural formula, but different spatial arrangement of elements. See Part 2. Explain with a reason whether the student is correct or incorrect. Well, the student is not correct because 2 groups of 1 carbon atom, so that carbon atom here has hydrogen there, and this group here, and the same as this carbon atom which has hydrogen there and that group here. The same group on other carbon atom. So hydrogen there. So same group here cannot form stereoisomerism. One of them has to be different, and then that may be able to form stereoisomerism. Question 16D. These older reactions are used in the synthesis of many important organic compounds. The disorder reaction of butyl 1,3-diene with ethene is shown below. This is butyl 1,3-diene and this is ethene, and that is forming this compound here. And the way that happens is Part 1. Add coil arrow to show to the diagram below to complete the mechanism for this disorder reaction. So this arrow is going there to form a bond, which means that we go there to form another bond, and that will break to form a new close ring bond, and that's how this is formed. So to add an arrow to this one, that's this. When that arrow goes there, this will break to form a new one here, and that will break to close the ring. So that will break here to close the ring, and this ring is formed. Part 2. 2 more disorder reactions of butyl 1,3-diene are shown below. In the boxes, draw the organic product for each reaction. Again, we are applying the same process where the alkene here will form a link, and this will break to form the new double bond here, and that will break to form a close ring. And so that's what we're going to draw there. So that's attacking there to form a link. That's fusion, and that will break, fission, to form a double bond there, fusion, and that will break to form a close ring, and that's what's formed. So that forms there, and a double bond is formed there. That's what you see in there. For the next reaction, again, that will form a link, and this will break to form a new bond there, and that will break to form a close ring. There's a close ring, and that's it. And then this will go there. And so this is what we're going to get. That is forming a bond, and this is forming a double bond here, and a single bond, and that will break to form a new bond here, and a single bond. And so that's what we're going to get. And this one is this one, and that one is that one, and this one here is forming that bond here, which is this one. And the double bond, single bond, double bond here is moved to there, and that will break to form a bond there. And that's what you call disorder reaction.